In this tutorial, we will be discussing buffers. A buffer solution is a solution that when small amounts of acid or base are added to the mixture, the pH does not change as much. The solution is resistant to changes in pH when the environment's pH is altered. A buffer solution is composed of a weak base or a salt of the conjugate acid, for instance NH3 and then the NH4. The weak acid with the salt of the conjugate base, for instance HF and then NaF. Notice the common ions. A buffer solution has a limited capacity, a buffer capacity. So in other words, if you add too much acid, then yes, it will be overcome, but small amounts, it will absorb the extra hydrogen or the extra OH. The concentration of the acid in conjugate base is not important. It's the ratio of the number of moles of each component. Diluting the solution does not change its pH. So let's think about this logically. If the pH of acetic acid and acetate buffer has the following concentration, we have 0.7 molar of the acid, 0.6 molar of the base. If the pH of the 0.7 acid is 2.45, predict whether the buffer solution's pH would be greater than, less than, or equal to 2.4. So, if we have acetic acid, and we're putting it in water, alright, so we have 0.7 molar of the acetic acid. Then we add, that alone is 2.45. Then we add 0.60 molar. We're adding base. So therefore, it's going to shift to the left by Le Chatelier's principle. That's making the solution smaller amounts of H3O plus, meaning it's going to be more basic. More basic means that the pH value is actually going to increase. Therefore, that 2.45 is going to go up when you add base. Let's do this mathematically just to make sure we're right with our reasoning. So what is the pH of a buffer with HOHC, which is acetic acid, Alright, so we have 0.70 molar of the acetic acid, and we have 0.60 molar of the acetate. The H2O is ignored because of the fact that it's a liquid, it's not an aqueous solution, and initially we don't have any of the H3O plus there. So we're going, since they gave us the Ka, we're going to say that it's going to leave as an acid and then add as a base. Okay, so we're going to do the equilibrium constant, so that means the right side over the left side. Alright, with those minus x's, we're going to assume that the amount that's disassociating is far smaller than the initial concentrations. Therefore, we're going to leave those out and we're going to double check our assumption in a minute. So let's go ahead and cross multiply the 0.7. That comes out to be 0.600 times x is equal to 1.26 times 10 to the negative 5. Now divide both sides by 0.6. Our x comes out to be 2.1 times 10 to the negative 5. You can see that the 2.1 times 10 to the negative 5 is far smaller than the 0.6 and the 0.7. But let's double check that. I'm going to compare it to the 0.6 because it's the smaller of the two. So 2.1 times 10 to the negative 5 over 0.6 times 100. That comes out to be 0.0035%, far smaller than 5%. So we're okay. We can take the pH of this now. The pH becomes 4.68, which we originally assumed it would be greater than 2.45. So we were right. Now there is an easier equation. This is the Henderson Hasselbalch equation. The Henderson Hasselbalch equation expresses the mathematical relationship between the acid and the base components of a buffer solution. It simplifies the pH determinations of a buffer solution with its final equation. The pH is equal to the pKa plus the log of the concentration of the conjugate base over the acid. The Henderson-Hasselbalch equation can be used to determine if the pH to determine the pH of a buffer solution when the initial concentrations of the two buffer components are greater than the Ka or the Kp value. The X approximation falls within this 5% rule. So that when we double check that, we need to make sure that this is okay, this is less than 5% before we can use that Henderson-Hasselbalch equation. So how does the Henderson-Hasselbalch equation relate to the pH of a buffer solution to its components? Well, let's take this one as an example. If we were to do the equilibrium constant of this, it would be the products over the reactants. So A minus H3O plus over HA. If we were solving specific is equal to the Ka. If we were specifically solving for the H3O plus, we could rearrange this equation by multiplying both sides by the acid and then dividing by the conjugate base. And that's how we get this. Note that the H3O, H, and OH are dependent on K, the Ka or the Kb respectively, and the ratio of the acid and base concentrations. The Henderson-Hasselbalch equation is derived by taking the negative log of both sides of the equation. So if we take the negative log of H3O plus, we're getting the pH. If we take the negative log of the Ka, we get the pKa. And then we have the negative log of the ratio. If we flip-flop the conjugate base in the acid, we turn that negative into a positive. And so that's how you get the pH is equal to pKa plus the log of the conjugate base of the acid. Note that the pH is determined largely by the pKa of the acid and then adjusted by the ratio of the acid to the conjugate base. The pKa and then the ratio. Using ice will never lead you to the wrong answer. It'll give you the right answer if you use it. The Henderson-Hasselbalch equation is just a simpler way of going about it. It's generally a good enough when the X is small, approximation is applicable. So if it's less than 5%. So in order to determine that before doing all the work, you have to look at the Ka and the concentrations. The initial concentrations of the acid and the salt are somewhat concentrated. That's what you want to look for. Or the Ka is fairly small. For most problems, this means that the initial acid and salt concentration should be over 10,000 times larger than the value of the Ka. The Henderson Hasselbalch equation is not to be used when a problem is asking you to determine the pH of a non-buffer solution. So these are only for buffer solutions. Alright, so let's do a practice problem. Determine the pH of a buffer solution composed of 0.25 molar HCN, 0.17 molar NaCN. So this is our acid, this is our base, and then here is our Ka. Look at the concentrations of the buffer components and compare the Ka value to the Henderson to determine whether the Henderson-Hasselbalch equation can be used to solve for the buffer's pH. So let's look at the concentrations first. The Ka is times 10 to the negative 10. The concentrations are 0.25 and 0.17. Those are much bigger than the Ka. So therefore we can use the Henderson-Hasselbalch. So that equation is pH is equal to the pKa plus the log of the conjugate base over that of the acid. So pH is equal to the negative log of the Ka, which is 4.9 times 10 to the negative 10. We got that from the problem right here. Plus the log of the conjugate base, which is 0.170, over the acid 0.250. So if we take the negative log of this, it comes out to be 9.31. Divide this out, comes out to be 0.68. The log of 0.68 is negative 0.167, and that comes out to be 9.14. And that's how to calculate the pH of buffer solutions and using the Henderson-Hasselbalch equation.